When we're talking about orthogonal, perpendicular, and normal, they're all actually talking about forming right angles, but orthogonal is when two vectors form a right angle. Perpendicular is when two lines intersect at a right angle. And normal is when a line and a vector form a 90-degree angle in the plane. Just like we know that two vectors are orthogonal if their dot product is equal to 0, we know that two vectors are parallel if their dot product is equal to the product of their respective magnitudes. We can say that the dot product of vector v and vector w is equal to the magnitude of vector v times the magnitude of vector w, or their dot product is equal to the opposite magnitude of vector v and magnitude of vector w times each other. Looking at this figure that we have a car that's parked on a hill. The angle of inclination of the hill is given by theta. And then we have this force vector that is straight down from the tire. We can break up that force vector into a vertical component and a horizontal component. The force that is required for the brakes to keep the car from running downhill is the opposite of F1, because F1 right now is the current force of the car, so negative F1 is going to keep the car from rolling down. F2 is the amount of force that the tires have to withstand against the ground. When you sum force vector 1 and force vector 2, because they are tip to tail, that gives you the resultant force vector F. We decompose force vector F into the two components F1 and F2, and we can calculate their individual measures. We can decompose vector F into the two vectors F1 and F2 that are orthogonal to each other by using what we call the projection onto that vector. I'm going to use vectors v and w to match what is given in the book. But on the right-hand side, you'll see these images where you have vector v1 and v2, where vector v1 is the projection of vector v onto vector w, and v2 is orthogonal to vector v1. And remember that vectors v1 and v2 summed together equal the overall vector v. When you're looking at the projection, when you're saying the projection of vector v onto vector w, the larger letter is the one that is being decomposed. So vector w is not the one that's going to be w1 and w2. It's vector v that's going to be vector v1 and v2. If you look at the figure, you'll notice that v1, which is the projection of vector v onto vector w, is parallel to vector w. Because they're parallel, then they must be equal with respect to some scalar c. We can say then that vector v1 is equal to some scalar c times vector w. In addition, vector v2 and vector w are orthogonal, and so their dot product must equal 0. That means that vector v2 times vector w is equal to 0. If I take the dot product of vector v and vector w, I can replace vector v with vector v1 plus vector v2, and then apply the distributive property to get vector v1 times vector w plus vector v2 times vector w, so that I can use some decomposition results. We know that the dot product of vector v2 times vector w is 0, so that means that the dot product of vector v times vector w is just equal to the dot product of vector v1 times vector w. Now we can substitute in c times vector w for vector v1 because they are parallel. And by properties of dot products, vector w times vector w is the magnitude of vector w squared. So that is c times the magnitude of vector w squared. We then have that the dot product of vector v times vector w is equal to some scalar c times the magnitude of vector w squared. Solving for c gives us the dot product of vector v times vector w divided by the magnitude of vector w squared. This information is summarized here in the chart where we have decomposition of a vector into orthogonal vectors. Vector v1 is given by the projection of vector v onto vector w, and vector 2 is given by vector v minus vector v1. So you solve for vector v1 first, and then you can find vector v2. We can use vectors to compute the work done on an object. Work is found by taking the magnitude of the force in the direction of motion times the distance that the object is moved, and work is going to be a scalar quantity. Since force is typically given in newtons, work is measured in newton meters or foot-pounds, depending on what the unit is that you're given, but those are two that are typical measurements. It's important to note that the magnitude of force has to be in the direction of motion. And if you're dealing with a force vector that is not directed in the line of motion, you only use the component of the force in that direction when you're calculating the work. You can see the definition of work summarized here. And in the figure, you see this vector D. It's the displacement vector. You are displacing something from one point to another in a straight line under a constant force F. So then you calculate work by taking the force vector times the displacement vector. If your force is not in the direction of motion, you would then calculate work by taking the magnitude of the projection of vector F onto vector D times the magnitude of the displacement vector. Or the work is calculated by taking the magnitude of the force vector times the magnitude of the displacement vector times the cosine of theta, where theta is the angle between vectors F and D.